Welcome to my video demonstration for the ACM SIGSPATIAL GIS Cup in 2015. The problem for this programming challenge, for this implementation challenge, was routing with polygonal constraints. And you can see this GUI which I implemented, in which you see a network, a street network, which has been taken from OpenStreetMap and transformed into shapefiles. And I've been implementing some algorithms in C++, which shall deal efficiently with dynamic polygonal updates. So when we zoom in here, you see a polygonal constraint, and currently constraints are not active, so we can calculate the shortest path here, and we see that if we go here and say that our search mode is with constraints, you see that this constraint is dynamically avoided. In order to implement this, I tried to use C++11 and template generic code as much as possible in order to get algorithms really readable. You should check out the source code to understand what I mean from that. I was using the Boost graph library for the graph, for representing the street network, and I also used Boost geometry to represent geometry such as line strings and roads, and for intersection. The user interface, which you see here, has been implemented with DSLab, which is a small library allowing you to write data science applications by just implementing a set of routines, one for rendering, one for creating a menu and reacting to it. And essentially, this boils your problems down to implementing only what changes for every time. You find that on GitHub. Please try it out also. For now, let's have a slight look at the data. As I said, it was taken from OpenStreetMap, and what you see here is the graph, the network graph. And you see that from these arrows that there are kind of one-ways represented. Other complexities of road networks have been taken out of the challenge, for example, turn restrictions and things like that, because there's no consistent way of dealing with them, and hence results of this challenge wouldn't have been comparable. So they have been removed from the challenge. What you see is a quite small network here, and that is the first observation towards what I actually did. For now, I think A star, the Boost implementation of A star, is active, and when we zoom out, you see the search space for this. It's essentially the black area. When we click somewhere to calculate shorter path here, you see that the search area, let's zoom in so that you see the shortest path. The search area gets smaller, but still it's quite large. Let's change from A star to Dijkstra, for example, the Boost library Dijkstra, and you see the search is getting slightly larger. So in order to speed up shortest path calculations in the presence with dealing with constraints, you either have to take a very complex indexing, which allows you to kind of reduce the black space, or to use some simple indices to do the same. So the complex indices, that are things that you calculate beforehand, and where for each polygonal avoidance you have to change the index. For this very small network, I didn't think that this makes sense. So I tried to find an index, or to use an indexing method which is compatible with increasing edge rates, and one of that is ALT. In ALT, landmark search, you create some landmarks around the map that are points, such that you calculate the distance from every other point to this location and from this location. And we can just look at it by creating some. Prepare landmarks. Let's prepare 5 landmarks now. So it takes 5 vertices, currently randomly selected, and calculates something for them, essentially the distance for each vertex. So now let's look at it. Let's remove the graph. You only see the shortest path now. And let's add landmark table 0. So this is a landmark which is located here in the blue area, and you see the distance increases gradually, and sometimes it's red, and you see that these are essentially not connected. Let's turn on the graph again. You see that from the landmark we selected, this area is not connected. So this is just a problem in the graph. This doesn't matter for our situation. It's not our system, it's just a data set. Okay, so let's remove the landmark table, and let's just look at the search space of ALT now. So search mode is again distance with constraints. Let me activate this just to be sure. And now the algorithm, let's activate ALT. And you see that the black area shrinks. And when we click around here, you see that it keeps small indeed. So let me zoom out so it's quite black. And let's now just compare to A star and just compare to Dijkstra, which is even larger. You don't see that really, it's just here a bit on this island. So back to A star, you see that it reduces it there. So you see that ALT is quite efficient, and ALT keeps valid with polygonal constraints. So let's add a polygonal constraint here. You can draw it actually. So this is a nice polygon. And now you see that the shortest path is like that. Let us move the search mode again. Distance avoiding constraints. Right. You see that this area has been avoided. And therefore, we do not calculate any new index. The ALT index keeps valid. It's just slightly less efficient. Look at the black area. And let's remove all constraints. And let's again search. You see that it's smaller. So the efficiency degrades while the shortest path is still found. And there is one final reason for using the ALT index on this graph, and it is the projection of the map. The map has been given in Web Mercator, so it's not very easy to calculate distances between points. And as the graph is quite small, or the research space does not increase that much, also due to these island connections, we have the situation that Dijkstra is faster than A star, because the search space of A star and Dijkstra is comparable. Dijkstra, A star, but A star involves distance computations for every vertex. For ALT, all these distance calculations have been reduced to table lookups, and we use some tricks in order to only use 3 landmarks at a time. So it's 3 table lookups instead of calculating distance in Web Mercator, which is not a very efficient operation. So you find the source code of this on my webpage, martinwerner.de, and yeah, keep tuned.